In 1985, he joined the Faculty of Physics at Yale University and moved to take his current appointment in 1993 as a Fellow of the American Physical Society and of the American Association for the Advancement of Science. Professor Krauss is the author of over 180 scientific publications, as well as numerous popular articles on physics and astronomy. In addition, listen to this now, he's the author of 6 popular books, including the national bestseller, The Physics of Star Trek, and his most recent book, Atom, An Odyssey from the Big Bang to Life on Earth and Beyond. He is the recipient of numerous awards for his research, writing, and lecturing. These include the Presidential Investigator Award given by President Reagan in 1986, the American Association for the Advancement of Science's 1999-2000 Award for Public Understanding of Science and Technology, joining previous awardees, Carl Sagan, Edward O. Wilson, and the 2001 Andrew Gaumont Award, given annually to a person who's made significant contribution to the cultural, artistic, or humanistic dimensions of physics. Previous awardees include Freeman Dyson, Steven Weinberg, and Stephen Hawking. In 2002, Krauss was awarded the American Institute of Physics, Science, and Writing Award for his book, Atom. Professor Lawrence M. Krauss.
That's nice to be here.
I understand you're here under somewhat unusual circumstances over on your end, huh?
Yes. It's every time I hear the lightning, it makes it very appropriate because I'm here in the dark. I'm at the University of California right now, and all of the power is out because of a fire. But remarkably, the phones still work.
The phones work. So, in other words, you're sitting at the university in pitch blackness?
You got it.
When did that occur?
About an hour and a half ago.
Where is the fire?
I phoned the police. It's somewhere in a parking lot. But somehow that seems to affect the power at the university, or maybe they turn it out for safety reasons.
At any rate, you're not in imminent danger of turning into a French fry.
If you hear me scream and run away. But I don't think so.
All right, good. Well, then it'll give you a nice, relaxed atmosphere to sit there and just sort of tell us everything you know in.
Yes.
Mm-hmm. All right. Professor, it's rare indeed and an honor to get somebody on the air with your kind of credentials, and so I've got a lot of very interesting questions for you, beginning with time. For me, personally, time travel has always been probably, the most intriguing thing I could even consider doing if I had anything I named that I wanted to do before my life ended. Traveling in time definitely would be up there at the head of the list.
Sure, well, you're not alone. I think everyone would love to go back in time and either correct the errors of their youth or relive them, depending on their mood.
Huh. I'm actually not sure that would be what I would do.
You go back and meet your favorite heroes from history.
The possibilities are absolutely endless, actually. So we've got a lot to talk about. In your opinion, is time travel ever going to be possible in either direction? Well,
what is fascinating about time travel, and it truly is fascinating, I mean, everyone's excited by the prospects, is that given the laws of physics as we now understand them, we cannot say it's impossible. And that alone is a remarkable statement, because there are lots of... The minute you allow for time travel, you produce a host of paradoxes, the most famous being the grandmother paradox. What happens if you go back in time and kill your grandmother before your mother was born? Well, then, of course, you couldn't exist, right? But if you couldn't exist, how did you go back in time and kill your grandmother? And that would give you a headache if you think about it long enough, and it gives physicists headaches. And so that's one of the many reasons why many physicists have presumed that a sensible universe shouldn't allow time travel. In fact, Stephen Hawking was when the physics of Star Trek came out, it actually caused a big stir in England, because Stephen had come out and said time travel is impossible earlier. And then in the foreword for that book, and as I argued in that book, given the laws of physics as we now understand them, you couldn't say it was impossible. And the London Times had a front-page story saying, Stephen Hawking changes his mind. I mean, he actually gave a very good argument for why he thought time travel was impossible.
Why did he thought it was impossible because of what you just described, because of the paradox?
Well, actually, he even said something more that maybe resonate with your listeners even more. He said, if time travel were possible, we'd already be inundated by tourists from the future.
Where are the time travelers, right?
Exactly. Of course, I countered him by saying they all went back to the 1960s and no one noticed. But in any case, there are many questions, and so if you're going to allow for universal time travel, you have to try and address those things. But the law, general relativity, as a theory, allows in principle for time travel. However, we know that in order for time travel to occur, then there must be very exotic types of energy that you have to be able to create, totally different than anything we know of normally on Earth or in stars, because in fact relativity tells us that space and time in fact respond to the presence of matter and energy. Mm-hmm. That's the aspect that space curves in the presence of matter. And time and clocks change the rate at which they tick in the presence of matter. In fact, a clock on the first floor of a building actually ticks at a slightly different rate than a clock at the top floor. That was one of the predictions of general relativity. It's a very, very small difference, but in fact it was measured in the 1940s and 50s for the first time with atomic clocks.
What about with respect to motion? I mean, those are two clocks that are not in relative motion. However, I understand they've taken two clocks and put them on jet planes going in opposite directions and measured a pretty significant difference.
Well, a measurable difference. I don't know whether you'd say pretty significant. You would notice it on your watch at home, but atomic clocks you can measure it. Yes, indeed, clocks. That was one of the first predictions of special relativity, and in fact, it's not a science fiction thing at all. We can measure it in undergraduate physics laboratories every single day.
Okay, let me stop you and just ask. Would the two clocks you described, one on the bottom floor and one on the top floor, would the delta or the difference be greater with two jet planes going in the opposite direction? If so, why?
Well, they're both very small. They're both about less than a part in a million in terms of the change, so that when one clock ticks a second, another clock is going to tick 1 second plus a millionth of a second.
Yes.
They're extremely small because in order to get measurable time differences, I mean significant, you either have to be traveling at very close to the speed of light, which is 186,000 miles per second, far faster than any jet planes, or you have to be in a gravitational field that's so strong, well, that it would kill you before.
Like a black hole.
Like a black hole.
But again, going back to my question, the clock in the top of the building versus the one on the first floor and the two airplanes, would there be a difference between those two measurements of difference? Would the jet planes achieve a slightly greater difference?
I actually think the jet planes traveling as they are at only maybe 600 miles per hour would actually have a smaller difference than
really?
Clocks, yeah.
Really?
Yes, because the actual the relative difference is actually related to the velocity of the plane over the velocity of light squared, and that's a very small number. I mean, light is it goes very fast. It 186,000 miles a second is pretty darn fast. That's 2 seconds to the moon and back, basically, and a jet plane at 600 miles per hour is much slower, and the square of that is very small. So that's why, in fact, it took a while before that hypothesis of Einstein's was directly verified. But now it's amazing. We can verify. In fact, anyone and I imagine among your listeners, there may be some people who indeed have Geiger counters.
Oh, yes.
We were just talking about radiation early on.
I have one. Yes.
And if you turn your Geiger counter on and move away from your walls, of course, there's radiation coming from walls and people and everything else. But if you go out in the middle of a field and turn your Geiger counter on, it will click. And one of the reasons it clicks is that there are cosmic rays coming from outer space that hit the atmosphere of the Earth and produce lots of charged particles that come down and make your Geiger counter click.
Professor, mine clicks inside. Every now and then I get a click from it. Now, should that be, or should the roof be stopping this?
Well, in fact, the roof does not stop some of these very energetic particles. In fact, there's one type of particle, an elementary particle called a muon, which is a lot like an electron, but about 100 times heavier, that makes it generally not just through your roof of your house, but actually deep underground before it actually stops. And the interesting thing about muons is we can create them in elementary particle accelerators on Earth, and we do it all the time. And we know exactly how long they live. They're actually unstable particles. They live 1/1,000,000th of a second on average, about. 1/1,000,000th of a second. But we can measure that. Now, the interesting thing is, these objects are created about 10 miles up at the top of the atmosphere when cosmic rays bang into the atmosphere.
Yes.
Now, you can calculate a particle traveling very close to the speed of light in 1/1,000,000th of a second will actually travel much less than 10 miles. Okay, it will travel probably only a few hundred yards, or maybe less than a mile. But these things make it all the way down to the Earth. How is that possible? Well, in fact, because they're going so fast, their internal clocks are ticking slowly, and they don't know they should decay. And so they make it down to the Earth. And so almost every time your Geiger counter clicks, you're proving special relativity.
No kidding.
Yeah, because literally those particles, it's what we call time dilation. Their lifetime, when they're moving very fast, is much longer than their lifetime when they're standing still, precisely because their internal clocks are slowed down.
So these particles should decay. I mean, in the world of physics, they should decay, but explain to me what you mean by they don't know they should decay and they're going so quickly.
Okay, what Einstein told us, let's take it back to something that's a little more personal, you in a spaceship, okay? Einstein told us that if you travel out in a spaceship and you're going very close to the speed of light, that if I'm watching you, your clocks appear to be slow compared to mine. So when my clock ticks, goes for an hour, your clock may only tick for a second. Okay? That's what it looked like. It looked to me like, oh, your clock is running very slowly. My clock has clicked 3,600 seconds, and yours has only clicked 1. There's something wrong with your clock. But what it really means is, in fact, that time is relative. That in your frame, for example, if you went to the center of the galaxy, which is about 40,000 light years away, and very close to the speed of light, if I were watching you, it'd take 40,000 years. Okay? It'd be pretty boring. But it'd take 40,000 years for you to get there. But in your frame, if you're traveling very fast, that whole trip could just take 2 weeks. And it really would. It's not science fiction. If you were traveling close enough to the speed of light,
yes,
that trip for you would literally just take 2 weeks. And whereas obviously for someone on the ground or a civilization on the ground, it would take 40,000 years. And so, and it's absolutely true that that's what would happen. And so for these muon.
So in other words, let me get this straight. You could take a 2-week trip, and now you're back, and 40,000 years have elapsed.
Yes.
On Earth.
Yes.
But you have only grown 2 weeks older. 2 weeks older.
Absolutely. That's the gist. That's been used by many science fiction writers for lots of good stories. Planet of the Apes, lots of famous science fiction stories are based on that idea. But it's not science fiction. It's really true. Of course, you have to be traveling very, very, very close to the speed of light in order to do that. And there's the rub, because to travel very, very close to the speed of light requires unbelievable amounts of energy. Einstein also, unfortunately, told us that the faster you're going, the closer you're getting to the speed of light, as you get closer and closer, not only do your clock slow down, but something else happens.
What?
You act like you're heavier and heavier. Okay, your mass actually appears to increase. And again, we measure that for elementary particles. Those muons, when they're traveling very, very close to the speed of light, act much heavier than muons that are at rest.
But, Professor, wouldn't it be possible, for example, with an atomic rocket, to build toward the speed of light, come pretty doggone close to the speed of light in continued acceleration?
Well, in fact, it would be. It's not impossible, but it would be very difficult. In fact, in the physics of Star Trek, I actually did a calculation that kind of surprised me. Even if we had fusion reactors, which we don't have on Earth,
right?
But fusion is the stuff that powers the process that powers the sun,
yes, and
thermonuclear weapons. It's obviously, as my friends at Los Alamos like to say, you get more bang for your buck from a fusion reaction than a simple explosion.
Yep.
1,000,000 times more power. So we can't control fusion right now. We have uncontrolled explosion. But let's imagine we had a fusion reactor and we used it to power a spacecraft. Well, every time you wanted to just do the following simple maneuver: start out at rest, go to, say, just half the speed of light, not 99% of the speed of light, but just half the speed of light.
Okay.
And stop again. Every time we want to just start, go to half the speed of light and stop.
Stopping is as much trouble as starting, right?
Exactly.
Yeah.
Every time you did that, you would need to find 7,000 times the mass of the spacecraft in fuel. And that's if you had a fusion reactor. Okay?
Wow.
If you used the conventional rocket fuel, I did a calculation which even amazed me, to take a single atom and accelerate it using conventional rocket fuel to half the speed of light would require more fuel than there is mass in the entire visible universe.
Mm-hmm.
So it's not, I mean, while we like to talk about this, it's not easy, because even if we had fusion, you'd have to take 7,000 times the mass of the ship every time you wanted to start and stop, if you powered the ship with fuel on board. And we can talk about that later. One of the ways around this may be not to carry the fuel with you, but be powered from somewhere else. Even if you used matter and antimatter, which are which give you the most bang for the buck in the universe, when antimatter exists in nature, and when a particle of matter encounters a particle of antimatter, the two annihilate, producing pure radiation, and that turns mass into energy with 100% efficiency, and you can never do better than that. Even if you did that, the amount of fuel required would be amazing.
Well, yeah, but a jet aircraft, for example, operating within the atmosphere, takes in air and blows it out real quick, right? Yeah. That's what a jet does. So why not imagine some sort of craft that takes in dark matter and spits it out real fast?
Well, real fast is the issue. The point is that a jet aircraft cannot travel a lot faster than the air that it spits out. Okay?
Right.
And in a fusion reaction, for example, the constituents after the reaction are moving about 3% of the speed of light.
Okay? Gotcha.
And so if you want to move faster than 3% of the speed of light...
then you need to spit faster.
Well, exactly. You need to spit faster. And, of course, the fastest you can spit is spitting things out at the speed of light. So like shining a laser beam.
Sure.
So, in principle, you'd say, okay, well, let's just shine a laser beam behind us and we'll start speeding up. And the point is you will, but it takes a long time because light, doesn't carry a lot of oomph. And so eventually, it's the most efficient way of going fast.
Light?
Just shining light behind you, basically.
I've got a Geiger counter here, and that beep you hear is the occasional little particle that comes crashing down. There was another one. You heard them two in a row. So if you have a sensitive Geiger counter, you can do that. Pretty strange sitting here and listening to that and knowing where it's coming from and how it made it here and all the rest of it. Professor, you're back on again.
Yeah, it's one of those fascinating things that it's nice to see a simple demonstration of such an exotic piece of physics.
Yes, and of course, these are handy little instruments to have around just in case of, I don't know, whatever might happen these days, huh?
Yes, yeah.
Yeah. So time travel then, it seems to me like the bottom line of all this is, you're saying, maybe it is possible with enough power. Well, yes, we haven't even, the kind of effects we've been talking about, clocks slowing down and speeding up, yes, are exotic and in fact require lots of power, but they still don't address your original question. They don't allow time travel backwards. They just mean that different people in different places can have their clocks move forward at a different rate. But to actually go backwards in time is even more exotic, and that not only requires lots of energy, but energy of a totally different type. It turns out that just speeding up or slowing down isn't good enough. Okay. You need something far more exotic, something that has what's called negative energy, in fact. And it's right now it's to some extent the stuff of science fiction. People have proposed, given general relativity, weird things called wormholes and shortcuts through space-time that might allow you to create a time machine, but in order to build these objects and actually use them, you'd have to have something that was gravitationally repulsive. And as all of your listeners know who've taken physics, gravity sucks. It tends to always pull. It never pushes. Mm-hmm. And in order to build a time machine, you'd have to have something that's gravitationally repulsive. We know that in general relativity. And the question is such material possible to create and build and use? Well, we don't know the answer. Wait, gravitationally repulsive. All right, fine. Why does that allow time travel in reverse?
Well, let's see. Well, in order to explain that, I'd have to give you an example of a time machine, which I'm happy to do if you want to work with me here.
I'm working with you.
Okay. So one good example of a time machine is something called a wormhole, which is sort of like a shortcut through space in the following way. Imagine a sort of a balloon.
A la Jodie Foster.
Exactly, a la Jodie Foster in Contact, exactly.
Yeah.
But the idea is general relativity says, well, space can be curved, right? So imagine a curved balloon. And if you were an ant living on that curved balloon, if you wanted to go from one end of the balloon to the other, you'd have to walk around the balloon, right?
Right.
Okay. Unless you're an intelligent ant who's taken general relativity. And then you know if you push down in the balloon, if you produce a lot of curvature in one place, and you push down in the opposite hemisphere, you push really hard, those 2 points can meet, and you can cut a little hole and sew it together and make a little tunnel, literally a shortcut from one place to another.
I've come to observe, Professor, that people of your sort work with ants a lot in analogies. They really have a lot of
they're oldies but goodies. What can I say? In any case, that two-dimensional wormhole is sort of an analogy to what might exist in principle in the real universe. If you put a lot of energy and matter in one place, you'd curve space tremendously. And if you might imagine somewhere ostensibly very far away, a similar thing happens, and somehow this shortcut connects these two places, like Jodie Foster's wormhole in Contact.
Yeah.
Now, it sounds nice. Now, the question is, could you actually build a wormhole? Well, the answer is we know you cannot if normal matter and energy are all there is. In fact, calculations have been done to show that the problem is if you put a lot of matter and energy in one place, it's gravitationally attractive, and it will collapse to form a black hole. We know that. As gravitation, it will collapse. Okay? And we can prove that at either end of the wormhole, the mouth of the wormhole will collapse into a black hole out of which nothing can escape in a time shorter than it takes to go through the wormhole. So there are no traversable wormholes in nature unless you have gravitationally repulsive material. Well, if you had that, you could fill the wormhole up with that kind of energy, and it would hold the mouth of the wormhole open. So you could create stable wormholes if you had gravitationally repulsive material. Now, what does all this have to do with time travel? Well, it turns out if you had a wormhole, you could have a time machine if you had a traversable wormhole. And here's the way. It's going to sound like a used car salesman, so just bear with me here. If you're at one end of the wormhole, and you're just sitting there, okay?
Yes.
And you have a friend at the other end of the wormhole on the other side of the galaxy somewhere, okay? And you look at a telescope with a telescope and you see her there at the other end of the wormhole, okay?
Right.
But her end of the wormhole is moving very fast. Say it's doing a big circle, say 5 light years around.
Okay.
Pretty quickly. And let's say that end of the wormhole is moving at near the speed of light, so it takes her 5 years to go around in that big circle, okay?
Right.
So you watch her. It takes 5 years for her to do that. Of course, she's at the end of the wormhole moving through space very fast, so her clock is traveling slowly.
Right.
So for her, that takes, let's say, 1 week. So now she is 5 years minus 1 week behind you in time.
Uh-huh.
And if all you have to do is walk through the wormhole and you come out the other end and you're 5 years earlier. And so the idea is if you had stable wormholes, you could in principle have a time machine. But as you can see, the problem is we know you cannot have stable wormholes with normal matter and energy. We know it. It's been proved mathematically. There's no doubt. So if you want to do it, you have to come up with some weird, very weird kind of energy, which is not like anything we create on Earth. And we don't know.
Yes. I want to ask you a question.
Yeah.
Is the creation... I've heard rumors, Professor, that there are people like yourself working on the actual creation of a black hole, or
a baby universe or wormhole.
Or even a sort of a replication of what they think might be the Big Bang and all that sort of exotic sort of stuff. Now, if they would have sudden success with this and they would create a stable... first of all, is it a really good idea to be trying that stuff?
Well, unfortunately, a lot of that is hype in the sense that we use those words to try and explain to people what we're trying to do and make it seem interesting. In elementary particle physics accelerators, we are in a sense trying to recreate conditions that were very similar to the conditions in the earliest moments of the Big Bang explosion.
Mm-hmm.
But it's wrong to say we're trying to recreate the Big Bang because we're not. The energies involved are minuscule in these accelerators, And therefore, the regions over which you would create any kind of conditions that are comparable to the early universe are so small, and the energy is so small, that they're irrelevant. The thing about our Big Bang was that the earliest moments of the Big Bang, and it is amazing but true, all of the mass and energy in our entire visible universe was contained in a region smaller than a baseball. Okay, everything, all the mass and all the stars and galaxies.
You do understand, don't you? The average person really has a hard time with this.
Of course, and not just the average person, but everyone does. It's hard, it's impossible to imagine how you could compress everything we see into such a small region. And it amazes me when I think about it. In fact, my book Atom, in a sense, was a way to try and personalize that, because it's a history of an individual oxygen atom in a glass of water that you're drinking tonight. A history of that atom from the beginning of the universe to the end, and I tried to sort of personalize it and make that atom the hero, because it's very hard in an abstract sense to try and imagine those configurations. But
are there words you could give us that would attempt to describe how something the size of a baseball becomes all that is and can be seen?
Well, I can. We can try and follow it back step by step and see what happens. I mean, the configurations you have to achieve are kind of amazing. For example, if you took the mass of our sun and compressed it down to the size of Manhattan, okay, then you could show that just a teaspoonful of material will weigh about 100 billion tons. Okay, and you might say that's just crazy. I can never imagine doing that. But nature does it all the time. When stars explode, the inside of a star the size of our sun collapses into an object the size of Manhattan in a period of a second, and we see it. When a star explodes and forms a supernova explosion, it happens about once every 100 years per galaxy.
Right.
So we see it. The inside of the star collapses to form something called a neutron star, which is so dense that all of the atomic nuclei in all of the atoms in that star are actually touching. And the whole star collapses from the size of larger than the Earth to the size of Manhattan in a second. And what's amazing is we can see it happen.
All right, but you've still got a long way to go.
Exactly, we've still got a long way to go before we work backwards. But let me say why we believe this fantastical story. Why it's not science fiction. The point is, if we assume the early universe was in that kind of crazy, intense, hot, very dense configuration,
yes,
then we can use the known laws of physics as we explore them in elementary particle physics accelerators and at nuclear reactors, etc., to try and predict what we would see. And the amazing thing is we can say, well, when the universe was 1 second old, it had a temperature of about 10 billion degrees, if this idea is correct.
Right.
And that happens to be at a temperature where nuclear reactions will take place. We can actually calculate it. If you start out with all this hot, dense configuration with quarks and protons and electrons and all flying around, and then let it cool down to 10 billion degrees, how much, as nuclear reactions happen, how much of the light elements would be produced, starting out with hydrogen and then helium and then lithium, etc.
Right.
And the amazing thing is we predict, on the basis of things we measure in the laboratory, we predict that roughly 25% of the universe should end up as helium, whereas only 1 part in 10 billion or so of the universe should be lithium, the next lightest element. When we go out and measure with telescopes the abundance of light elements in the universe, what do we find? 25% of the universe is helium, 1 part in 10 to the 10th is lithium.
Okay.
Predictions that vary by 10 orders of magnitude are bang on with observations.
Okay.
We also predict there should be a hot afterglow of the Big Bang.
There
in 1965, it was discovered in, of all places, New Jersey.
Right.
And every single prediction we can make on the basis of that idea is an agreement, an exact agreement, with every observation we make about the universe. And so, therefore, if it quacks like a duck and walks like a duck, it's a duck.
Well,
I mean, and you could say, well, maybe it's not. And the point is, one of the biggest misconceptions about science is that people think science can prove something to be true. It can't. It can only prove something to be false. And it's false if it disagrees with experiments. There could even if a theory agrees with every observation you can make, there could always be a new observation down the line that would require you to revise your theory somewhat. It wouldn't make it wrong. Newton's laws are not wrong. They still apply today, just like they were when Newton developed them. But at the extremes of scale and extremes of speed, we've had to revise them a little bit. Einstein had to revise them at one scale and quantum mechanics at another.
Let's say that you physicists, theoretical physicists, can get us back to a baseball and to 1 second after the bang, about the temperatures and everything. But then just leaping across that 1 second, then you get like to the God second, don't you?
Yeah, well, exactly.
Or do you? In other words, is there a point where you say, sorry, this doesn't have explanation?
Absolutely. I mean, that's what makes science interesting. We don't understand everything. And so we fully know that the laws of physics as we now understand them cannot be applied before a certain time.
They began at that instant. The present laws of physics began at that instant. But
they began at that instant, but we don't know. In fact, we don't even know if they began at that instant. We know that they break down. They begin to make predictions that are nonsensical before a certain time, and we know that we'll need some new theory that will allow us to extrapolate back earlier. So we have many ideas of what that theory might be and what the predictions might be, but we really don't know.
Would you want to give me your best guesses?
Well, one thing that I think is quite reasonable, although it sounds like a cop-out, and here I agree with my friend Stephen Hawking, that if you ask sort of what happened before the Big Bang,
yes,
the answer is that's not a good question. Because what general relativity tells us is that space and time are tied together, and they're tied together with matter.
Well, that's not a good question for you.
Oh, yeah, no, hold on. Okay, yeah, exactly. But the point is, when things get very, very dense, it could be that what we mean by time, the whole notion of time breaks down. And time itself may have begun in the Big Bang. And so there was no sense of time before the Big Bang.
Well, how could there be? Must there not be two objects with relative velocity to each other to have the beginning of measurement? So if there was nothing, there could not be time.
Well, no. You see, the problem is let's step back and think. What does it mean to have relative velocity? That means they're moving apart in space, right?
Well, how do we measure time? The way the sun goes around, the Earth goes around the sun,
exactly.
Or the moon goes around the Earth, or whatever.
Motion is the way we measure it. Exactly. Yes. But motion requires moving through space.
Yes.
But it could be at very, very earliest instance when all of the mass of the universe was in a region smaller than the size of an atom, that space itself, the concept of space itself breaks down. It's not a good quantity. We don't know. We know that if we take the classical notions of space and time and try and apply them back then you get nonsensical predictions. And so it could just be that a better theory of space and time would give us better predictions. Or it could be that space and time themselves actually grew out of the Big Bang. And therefore, the classical notions that we use to describe the reality we experience don't apply back then. Just like at quantum mechanical level, just like at the level of individual atoms, many of the classical notions that are associated with motions of a baseball and when a batter hits it don't apply anymore when you're talking about electrons and atoms. We've had to learn that, our myopia, our cosmic myopia is revised. It's one of the greatest things about science. It forces us to realize that the way we view the world and what we think is sensible need not always be right.
Well, Professor, do you contemplate the probability of a giant nothingness prior to that instant, a giant waiting theater for the paints to be applied?
Well, actually, my favorite picture is probably that, in fact, that our visible universe is really just part of what might be called a multiverse, where there are regions where there are big bangs happening right now, an infinite universe where there are big bangs happening, there are big crunches, their universe is collapsing down to singularities, and in these multiverse, we happen to live in an infinite region, by the way, an infinitely large region, which happened to have a big bang 12 to 15 billion years ago. But there are other regions of this multiverse that are just now experiencing big bang, and I think that the laws of physics, we understand them, suggest that that's the most likely possibility. But really, right now, we're talking about metaphysics.
Well, while we're on the subject of multiverse, let's consider time travel and that nasty problem with Grandma. Well, in a multiverse, we go back and we kill Grandma, and in one timeline, in one universe, you pop out of existence as Grandma dies. Now, in the other instantly created universe, it's a different story altogether.
You're right. I mean, that has been proposed as one of the ways around this paradox.
Is it, do you think?
Well, it's nice words. The problem is, as far as I know, there's no physics behind it. I mean, for example, we know, people talk about the many worlds interpretation of quantum mechanics, that when you go back and, that whenever you measure something, you sort of have a lot of different levels of reality, and it's all nice words. But one of the things that is important about quantum mechanics is it never allows you to jump from one to the other. So it's one possibility, but right now there's no concrete physics that allows for such a possibility. And therefore, it's a nice idea, but there's no basis to that idea. That doesn't mean it's wrong, but right now it's just talk. Okay?
Oh, okay. Well, then let's say we take our little stroll through the wormhole, and we do, in fact, kill Grandma. Then that's a big problem, then.
It is a big problem. And here's another, it is a big problem, but people have come up with another solution,
and that
is that you're doomed to repeat the events of the past, namely, that, say you want to go back in time and kill Hitler, okay?
Yes.
Before he, did all his things.
Yeah.
Well, you go back in a wormhole and you do it, but just when you're about to pull the trigger, you trip, okay?
Yeah.
And that you're doomed, that the laws of physics are such that whenever you go back in time, you cannot change the future.
Professor, you were saying there might be another way to avoid the grandmother problem. I threw up the multiverse idea, or the new universe idea, I guess, instantly when you pervert what was supposed to happen. What other way might there be?
Well, it's the boring way.
There's a boring way?
Yeah, as they say, they call it in Star Trek a causality loop. I like that. It's better than the way the physicists call it. But basically, it's that every time you go back in time, you just repeat the same future, sort of like Groundhog Day. And you just repeat. You can go back in time, but you have to repeat exactly the same events the second time around, and then it's sort of not like it's not very much fun.
But
I mean, those are the only two solutions of that grandmother paradox that I know of. That, of course, the great thing about nature is if there is time travel, if it is possible, and we don't know, and that doesn't mean it is possible. It may be impossible. What it really means is we don't know.
Okay, I'm still not grasping though. You said you would endlessly be repeating that action.
Yeah.
How would that work with respect to the linear time that's going on in the world and the events that are going on in the world?
Well, it just means time would be circular instead of linear.
Circular. It would become circular only for you, or it would become circular for all?
For presumably for all.
Oh my God! You mean so one person going back and blowing it in time could put the whole world in this circular, repetitive, and never-ending loop?
At least, yeah. Well, at least the world is that person's experience.
Oh my!
It would mean that nature itself, because remember, space and time are both dynamical in general relativity, and so you can go through a circle in space, and in principle you might imagine you go through a circle in time, but if space-time is circular, then it's a property of space-time, and so, it allows time travel, but it doesn't, but it's very specific about how it allows it, so...
Well, they do say history repeats itself, right? So maybe somebody already blew it for us.
Exactly, maybe.
But that really... That's a kind of a pathetic ending for the world, isn't it?
Well, it's sort of not what you'd like with time travel.
Yeah, that's right.
And as I was about to say, that if time travel is possible, the real solution to the grandmother paradox is probably something we haven't thought of at all. And that's what I always find fascinating about nature is it tends to surprise us. And so, if I had to bet, I'm betting time travel isn't possible because it just seems so difficult to imagine resolving this issue, and I'm talking about it in principle. I mean, even if it were possible in principle, I have to say that we know that we've already been able to calculate how much energy would be required to, make a wormhole or do that kind of thing, if it were possible.
Yeah.
And even if it were possible, the energy required would be so immense, it'd be more than the mass of our galaxy, and so we're talking hypothetical here. And that's what people should realize. I always worry when one talks about this that people think that, and NASA, spending money trying to build warp drives, but it's kind of a waste of money at this because We're talking issues that are hypothetical right now, not things that you can have an engineer, sort of develop a new kind of box to do right now. And so these are fascinating questions, I happen to think, and I hope your listeners do. But they're issues that involve questions of principle that are not right now or in the foreseeable future practical.
What would be required would be an unimaginable new power source. But don't we have a habit of running into these unimaginable new power sources?
Well, we do have a habit of being surprised. We have a habit of running into new things in the universe, that's right. It would have to be an unimaginable new power source of it, but not just of regular power, of a kind of energy that is different than any kind of energy that we see anywhere in the universe, except in one place.
Yes, but if you go back to the early days of dynamite, let's say, that in actual years, it wouldn't be that long ago, right? Mm-hmm. And you were to demonstrate nuclear power to those folks. It would be unimaginable. It would be magic.
Absolutely.
It would be alien, perhaps.
Oh, absolutely.
To them, as unimaginable as this new power source we're speculating about.
Yeah, that's true, and so that doesn't mean such things can't exist. However, it is important to realize that we have, with our telescopes and other apparatus that we have in our laboratories, been able to explore the universe, in fact, observe the universe out to distances of billions of light years away.
Yes.
And the amazing thing that we happen to have discovered is that the laws of physics are the same everywhere. And we understand how stars work. And so if there were incredible new power sources, we should be able to see them, if you wish. And the nice thing about the universe is it's big and it's old. So no matter how crazy something is, if it's not impossible, it happens all the time.
Right. How does this... let's slide right in to the question of whether there's probably life out there or not. Statistically, with what we know about the known universe and the physics of everything, you said appears to be the same. Wouldn't that make it pretty, in fact, more likely than not, when you crunch the numbers, that there is going to be life out there, almost definitely, in fact?
Well, I don't know whether almost definitely is, but I'd say if you asked me, I'd bet that there's life out there, yes. I would say, given the fact that we know from our own experience that all you need to have life is water, solar power, and organic materials. I mean, on Earth, life originated about as soon as the laws of physics would have allowed it to. Within 100 million years of the time the Earth cooled down enough to be stable for organic reactions to occur, life formed. And so it seems to be fairly ubiquitous on Earth, and therefore, and one of the things we do know about space is that all of those things exist. We know there's lots of water, we know there's lots of starlight, and we even know there's lots of organic materials. One of the things we learned from the Hale-Bopp comet was not that there was a spacecraft behind it, but rather, when we looked at the spectrum of it, it actually had complex organic materials, the basis of amino acids. And so all of those things exist throughout space. And so I have a hard time believing there isn't life elsewhere in the universe. Now, the question is there intelligent life? That's a much more difficult question because we don't know that intelligence is an evolutionary imperative. I mean, we're here by a series of sort of cosmic accidents. An asteroid that just killed the dinosaurs 65 million years ago made room for mammals, and we happen to be mammals. Now, maybe that there are other ways to intelligence. We don't know how it works, so it could be that there's lots of life in the universe, but hardly any of it is intelligent.
Maybe the dinosaurs weren't just given a long enough run.
Exactly, that's true. We don't know. It could have been that if they had been, they'd be watching I Love Lucy now, but we don't know. And so I'm willing to believe, even if intelligence, however, is very, very rare, that there's still intelligent civilizations out there. I think that's not unlikely. What, however, is extremely unlikely, in fact, so unlikely as to be virtually impossible to imagine, is that those intelligent civilizations are coming here right now, or have in the time we've been cognizant.
Why is that hard to imagine?
Well, the point there's lots of reasons, but let's work through them.
Sure.
First of all, as I've tried to explain earlier, to go at anywhere near the speed of light,
yes,
requires an incredible amount of energy.
Mm-hmm.
Okay, so you'd have to basically harness the power of a star to take a spacecraft that would, take people or any beings that are sort of our size and move them from one place to another near the speed of light. Now, that's not impossible. You could imagine some civilization that's incredibly advanced could harness the power of a star and do that.
Well, let's think about that for a second. In other words, is that likely that there would be such a civilization, such an advanced civilization? The Big Bang occurred, 15 billion or so years ago?
Exactly.
Now, that's a lot of time relative to that 15 billion year mark. There's a lot of material way the hell out there that's been around for a lot longer than we have.
Exactly. Our sun is only 5 billion years old. So we're newcomers.
So there would have been lots of time for...
Yes. You also have to ask the question, and we're a good test. We're the only test case we have. Do intelligent civilizations survive for billions of years?
Oh.
And that's and you talk about your Geiger counters, the other things. You got to ask the question: do intelligent civilizations kill themselves off before they ever get to the point of being able to do that?
Yeah.
A lot of people think that's quite likely.
More than likely.
But maybe they do, and maybe there are intelligent civilizations that have been around for billions of years and are presumably, therefore, incredibly advanced. But even if they could harness the power of a star,
yes,
it would be hard to imagine why they would do that, take all of that incredible energy and resources that would be required. I mean, whether it's money or whatever else, fuel is money. The incredible resources it would take to basically demolish a star and use it for space travel, to come all the way here just to do kinky experiments on psychiatric patients of some Harvard psychiatrists, it just hardly seems an appropriate use of resources. First of all,
have you had any good heart-to-hearts with Dr. Mack? Have you?
Very brief ones. I've talked to people who more than Dr. Mack, with people who have either claimed to have seen UFOs or been abducted. And I think the point is that, and this is hard to say and hard to explain appropriately. It's not that I can say that those things are impossible or they didn't happen, because God knows I wasn't there. But you can ask, what is more likely? Is it more likely that that basically the laws of physics are being twisted and distorted and aliens abducting people, or is it more likely that people are in one way or another imagining that or dreaming or whatever? And you have to say, at some level, when you look at the implausibility of interstellar travel being incredibly expensive and incredibly energy consumptive is one problem. But the second problem is the distances are huge. And even if you were traveling at the speed of light from a star system, and the nearest stars are that might house civilizations are probably tens of light years away. Well, in 1947, when this famous Roswell incident was supposed to happen, there would have been no way that they would have known there was intelligent life on Earth, right? Because we hadn't been broadcasting signals long enough to get there, even at the speed of light, and for them to hop on a spacecraft at the speed of light and get back here in time for not to be here for 1947. Much less the fact that we're one of 100 billion stars in a galaxy that's 100,000 light years across, and even if they were able to detect our signals, well, it's pretty hard because we're in Cleveland. We have, where I live, there's 200 stations on TV. I can never find what I want before the program's over. In the real universe, there are an infinite number of frequencies to broadcast at, and so the likelihood, I believe it's worthwhile listening for a signal for extraterrestrials. The likelihood of detecting it is very small. But if you think about it, by the way, if you want to somehow discover life elsewhere, it's a lot easier to send out signals, radio signals, than it is to send out spacecraft. So by far the most likely way of making first contact is not by sending out spacecraft. So it's very inefficient. First of all, it takes a lot of energy. Secondly, to explore even the nearest star systems would take hundreds of years.
Agreed.
With a radio signal, as you know from the fact that you can broadcast so effectively throughout the United States, with a single signal going out in all directions, you can reach all of those stars And so it's a much more efficient way of trying to communicate. But even there, the odds are so stacked against us that while I'm fully supportive of SETI, because I think it's interesting, the likelihood that even if there are civilizations out there that will detect them is extremely small. Let me give you an example that hopefully will bring this home. Say you lived on a star somewhere else in our galaxy, and someone told you where to look for us. Okay? Someone said, look at that star over there in the corner, and look at the third rock from that star.
Right.
Okay? And you'll find life. And that even if you were told exactly where to look among those 100 billion stars, even then the likelihood of finding life on Earth at any given time is almost zero. Why? Well, if you've been a civilization that's been around billions of years longer than us, you could have watched the Earth from the time it formed to now, 4.5 billion years, and you could have been listening. And only during the last 30 or 40 years at most would you have had the possibility of hearing a signal. So even if you knew exactly where to look, and exactly what to listen for, and exactly what channel to listen to, you have a probability of 30 years out of 4.5 billion,
right?
Which is less than a chance of 1 in 100 million of detecting life on Earth when you know what to look at. We don't even know where to look or what to listen for. So it's a huge long shot to even communicate, much less travel to
well, as you know, the SETI group was looking very near mostly the hydrogen frequency. Now, yes. SETI has begun to move toward optical SETI.
Yes, and a lot of people think that's a good idea.
Are you one of them?
Well, I think to the extent that you can explore a lot of different frequencies, that's the way to do it. I mean, you want to have every window you can. The problem is it costs money. But I think an optical, I think that's a good idea. I mean, I think hydrogen is also a good idea because the reason, for your listeners who haven't thought of this, and probably most of them have heard this before, but the reason you want to look near hydrogen is that hydrogen is the most abundant element in the universe, and any technological civilization knows that.
And so it's a big marker.
It's a big marker. And so it's a very sensible idea, but it may be wrong. It may be that other civilizations want to have a searchlight or like a lighthouse or something. But what you have to realize is that all of this is worth looking for, but the odds are very small. And as small as the odds are of communicating, they're almost infinitely smaller of actually traversing in a realistic time.
When you look at our present civilization and the direction we're moving right now, for how much longer do you think we will be emitting immense amounts of electromagnetic radiation? In other words, radio, television, 100 years from now? 200 years from now? Will we still be, are we going to be in the old mode of broadcasting in the air? Are we going to have radars running? Or in another 100 or 200 years, will we have moved totally past all that?
Well, of course, the great thing about the future is one doesn't know what's going to happen. But I think it's reasonable to assume that we will continue to broadcast and use electromagnetic radiation to communicate. It's the most efficient way to do that. But what we'll find probably is the power outputs we need to generate are smaller because we'll find more, we'll be able to develop more efficient receivers. But I mean, radiation, we can detect electromagnetic radiation very efficiently. If with the Arecibo radio telescope, if there was a light bulb on Jupiter emitting radiation with the 100-watt light bulb, we could easily detect it with the Arecibo radio telescope. Electromagnetic radiation is incredibly easy to detect. And so,
yes, but what I'm saying is the human race may not stick with it for that long, relatively. I mean, a few hundred years, maybe.
Maybe, and if that were the case, then of course it makes the situation even harder. Right?
Well, unless we learn to look at some other frequency or something. Not only is the Big Bang, did the Big Bang occur, but everything is now beginning to actually accelerate away from everything else, so that in the end, it's going to be kind of a thing where I actually read a story where the light from distant stars will begin to blink out. The night sky will begin to save that which is really close to us. The night sky will begin to be devoid of stars. Everything will move away from everything else until we finally freeze to death in the darkness.
Yeah, I think I wrote that.
You wrote that? Yes. That was you that wrote that, huh? That's pretty graphic stuff, Professor.
Yeah, it's the future. Well, it is indeed one of the biggest surprises in the last century that when we look out, it looks like the expansion of the universe is indeed accelerating, which is crazy. It's insane, right? Because gravity, as I said before, is supposed to be attractive. It's supposed to slow down that expansion.
Right.
But there does seem, on a large enough scale, to be some kind of cosmic anti-gravity, something that's causing the universe to accelerate. And we know what kind of stuff will do that. It's crazy. If you give empty space energy, if you associate with energy with empty space, and by empty space I mean nothing, no particles, no nothing, nada, but empty space, if you give it energy,
yes,
then that energy, according to general relativity, is gravitationally repulsive. And it will cause the universe to accelerate. In fact, Einstein postulated such stuff early on when he called it his biggest blunder. He invented something he called the cosmological constant, because originally when he developed general relativity, we didn't know the universe was expanding at that time in 1916, and his theory was the same as Newton's theory. Gravity sucked. It said that you couldn't have stuff just sitting out there. Gravity would be universally attractive, and therefore everything would collapse together. And in his universe at the time, it looked like the universe was just sitting out there. And so he said, well, let's add a little repulsive force, give empty space this kind of energy, and it'll balance on large enough scales the gravitational attraction of distant stars and galaxies, and everything will just sit there. And then we discovered the universe was expanding, and you didn't need that extra force, because if the universe is expanding, well, gravity can be universally attractive and simply slow the expansion. So Einstein said, gee, I wish I hadn't invented that thing. Was my biggest blunder. Well, his biggest blunder may have been saying he was blundering, because, in fact, it looks like, what we're seeing today is it looks like the universe really has exactly the kind of stuff that Einstein first postulated, and we don't understand what it could be or how it got there, and, in fact, we don't understand anything about it. It's the biggest mystery in physics and astronomy, and that is incredibly exciting. I mean, because, again, what people seem to think of as scientists like to understand things. Actually, scientists like to not understand things because it gives us something to do.
Yeah.
And this is the biggest mystery in nature.
So it means there's a force out there throwing everything apart that we don't even begin to understand, put succinctly.
You got it. It involves very little energy. Let me point that out. I mean, even though it's making the whole universe expand, the density of energy that would be required to make that happen is so small that it would not be noticeable on Earth. Okay, I mean, empty space would have an energy which is like the equivalent of a mass of 10 to the minus 30 grams per cubic centimeter in energy, and that's very small. That's the equivalent of having one proton per every cubic meter of material. It's almost nothing. So on our scale, it's not noticeable, which is why it escaped our notice for so long. But when you build it up on large enough scales, there's lots of empty space out there, then it begins to have an effect. And the effect is, but there's one thing that you said, lest your listeners get too depressed. If the universe is indeed accelerating, it is true that stars and galaxies that are far away from us now will be eventually moving away from us faster than the speed of light.
Yes.
Because that's allowed, by the way, in general relativity.
And so when that begins to occur, we can't see it anymore.
We won't be able to see them. That's absolutely right. But the stars in our galaxy will never do that. I mean, until they burn out.
Well, I know, but that's going to be relatively close by. All that nice full sky that we get now, the Milky Way and all the rest of it.
Exactly. I mean, so the stars in our night sky are not moving away from us. They're trapped in our galaxy. But, of course, the point is they're going to burn out anyway, so the sky will get dark in our galaxy because the stars will burn out. But it is really amazing that in a period, in a cosmic sense, and people like me who worry about cosmic time have thought a lot about this. In fact, I've written scientific papers on this, that in a relatively short time frame, in the period of 10 to 100 billion years, which may sound like it's, not worth thinking about, but in fact, stars will still be burning, astronomers could still be around, civilizations much like our own could still be around 10 to 100 billion years from now, because there'll be stars just like our sun burning.
Pretty optimistic.
Yeah, well, maybe it's optimistic, but in that time frame, in 100 billion years, most of the rest of the universe will disappear. And in fact, the longer we look, we used to think the longer we looked, the more we'd see. We now know in 100 billion years from now, astronomers will sort of be out of business in the sense that they won't be able to see anything outside of our own galaxy. That's the bad news. The good news is, of course, I've tried to argue to Congress that we should fund astronomy now while we have a chance to do it.
Using that argument, huh?
It doesn't work, of course, because for a congressperson, the long-term future is 2 years.
Yeah, I know. I know. Well, all right. There's a rumor going around, and there are people going around saying that there is a planet out there just beyond what we can generally see, which they're calling this mysterious planet X. Mm-hmm. And it's supposed to be some large planet or perhaps a dying sun, which some believe comes swinging by Earth every now and then, causing varying degrees of trouble depending on how close it gets. But actually there have been stories, ABC ran one, that they did indeed spot something out there that does kind of look like a dwarf, burned-out sun or something or another. You know anything about that?
Well, I've heard rumors about various things. I do know that in fact, I mean, there can be lots of, as you probably know, what we define by a planet is changing all the time. Some people like to call Pluto a planet. Some people in New York City, for example, they don't call Pluto a planet anymore at the planetarium there, much to the chagrin of people. There are lots of objects farther and farther out.
Do you think they have any right to strip Pluto of its planetary status?
No, I don't think so.
It seems raw to me.
Yeah, I'm totally against it.
Okay.
I like Pluto, in fact.
Yeah, I do too.
And but there are lots of other objects out there further than Pluto in our solar system, and what you call planets, and what you if they're smaller than Pluto, are they a planet? So and as our telescopes become more sensitive, we can find dimmer and dimmer objects. But a star has a lot of mass and has a lot, and whether it's faint or not, it produces a significant gravitational effect, and therefore nearby in our solar system there are no other stars because the gravitational effect would be just huge. Now we are detecting farther away. We are beginning to be able to detect objects that are very dim. That may be failed stars, but they're not. Yes. They're not going to affect they're not affecting the dynamics of our solar system.
Well, let me ask you this: is there such a thing as a rogue planet or a rogue star? In other words, something that is traveling independent of other immediate objects that it's been affected by?
Well, in a sense, yes, we all are. I mean, in our galaxy, this is another thing that's kind of interesting for people to realize is that we're moving relative to background stars because we're all moving around the galaxy, but we're moving independent of each other. So in fact, stars that are nearby us now will in 100 million years be on the other side of the galaxy. So we're moving apart from other solar systems, and there are stars that are moving close to us, and there are stars that are moving far away.
Yes, but a fairly close call has fairly profound.
Oh, absolutely.
Right.
Absolutely. If a star approached, if another stellar system approached, even 50 times the size of our solar system, it could perturb the dynamics of our solar system and kick out some planets. And people have done calculations of what would happen if a stellar encounter occurred. And of course, what generally happens is things get kicked out, and planets get thrown out, and orbits that are now stable become unstable.
Very, very profound effect. So, would we see this coming, or could it come to be a surprise for astronomers? Are we watching the relative velocity, or relative to us, of everything out there, so that we're so sure this wouldn't surprise us one day?
Well, with stars, it's not a worry. I mean, at least in a cosmic time, we don't have to worry. But smaller objects, we certainly have to worry about. There are 1,000 objects, small. I'm talking about asteroid-sized objects, 10 kilometers and larger, that are known to exist in that are on potential Earth-crossing orbits, and we, with absolute certainty, we can say that we're going to be hit at some point in the future, because on average, an asteroid that's 10 kilometers or larger hits the Earth about once every 100 million years. And the last big one we know of was about 65 million years ago. So depending upon whether you're a betting man or not.
Well, but suppose there were something as large as a planet. And we haven't seen it all yet. So
yes, but we can in fact, but we know for certain that in the region within the distance of Neptune to us, okay, there are no other planets, okay?
Yes.
And no other objects as massive as Pluto or larger. And what's amazing is with our telescopes we can actually see objects that are much, much smaller than Pluto, as I say, asteroid-like objects that are extremely distant, and therefore it's hard to imagine that something with the mass of a planet that's close enough to have impact upon us in a kind of century time scale or two would have escaped our notice. But there are many objects that might have. I mean, just a 10-kilometer size object is pretty bad.
What about something with a return time of say 3,600 years? I mean, that is possible, isn't it?
It would be possible, except if it were massive enough to impact upon us in 3,600 years. The last cycle around, it would have been massive enough to cause to dramatically perturb the Earth's orbit.
Oh yes,
and we know that it didn't because of the fact that life and many other tests we can do tell us that the climate on the Earth has changed, but not that radically.
Well, yes, but what I'm saying is perhaps this 3,600 years, it would be a bit closer than it was last 3,600 years. That would change, would it not, to some degree, past pass?
Yeah, I mean, it's not impossible.
Yes.
It's highly unlikely, but it's not impossible.
I see.
Because you have to have it change dramatically from one over to the next, and you could always imagine things get perturbed by something else, and that you don't know about, and their orbit changes dramatically, and suddenly they come a lot closer, and I mean, so it's impossible to rule such things out. It's highly unlikely. It's much more likely that we'll get zapped by something smaller, which would still be pretty darn bad.
Oh, sure. Something the size of what happened to the dinosaurs would do nicely. Yeah. I'm sure. Are we prepared to stop something like that now if we saw it coming?
That's an interesting question.
Yes,
I mean, there have been those movies, and if we had, it's not impossible for me to imagine that we would be able to do something if we had enough lead time. Because, you need 10 years lead time probably.
Like what?
How to stop it?
Yes.
Well, I don't think Hollywood got it that wrong. I mean, if you have enough lead time, you could imagine having a spacecraft have an encounter with the object and do one of many things. Either of course, have nuclear explosions and somehow break it up, or perhaps that slowly divert its trajectory just enough so that it misses the Earth. But you need a lot of lead time, and 6 months ain't going to do. And that's why it's important, and by the way, we are doing it, to have a network of telescopes looking for such a thing.
Indeed, yes, but more times than not, Professor, I read the news stories here on the air, so I know. The news stories read, yesterday, Earth had a close encounter. Or they read, last week, astronomers now tell us Earth had a very close encounter. And so, you're saying if we had 10 years, a lot of times we don't even know we've had a close encounter until after.
No, I think what the news stories say is that yesterday someone discovered an object that might have a close encounter with us. And by close encounter means pretty far away, by the way. The good news is that we're a pretty small target in a pretty big space, and that's why these things on average don't happen very often, fortunately for life on Earth. And what is true is that we already have found 1,000 objects that we can monitor and know their trajectories. And with a good deep space telescope network, we could probably pretty effectively monitor almost everything that is likely to impact upon us in 10 years.
Well, how come mostly amateurs discover all this?
Well, the nice thing about it is it takes patience, but it doesn't take huge telescopes. You don't need the Keck telescope to do this.
Yeah, I know, but by the time you're the size for Frank's telescope, you don't have 10 years.
Well, you actually, for most of these objects, you probably do. But what you only have 10 years if you get all of them. That's the point. For any given object, it's unlikely it will hit us within 10 years. But if you want to be certain that you're safe and that you're not missing anything, you have to scan the whole sky, and that's what an amateur can't do, because you have to have a network that constantly scans the whole sky, and therefore you have to have a coordinated network of lots of amateurs, if you wish, or a bunch of professionals. And so people have said we should have a coordinated deep space network, and it's not that expensive, and it's happening, and I think it's obviously useful that it happened. But the good news is the likelihood is extremely, extremely small, because the average impact time is 100 million years, and that means in any given century you got a chance of 1 in a million of getting hit.
Huh.
And so, you know, that's pretty good odds.
Those are good odds for us, but cosmically they're pretty bad odds. And
they're pretty bad in the sense that we will definitely be hit in the future. And it's, you know, there's going to be a lot of things in the future that are going to be challenges for life. And an impact by a comet or an asteroid is certainly one of the long-term potential disasters. There are a lot more if you actually think about it. In one of my books, I sort of start thinking about all those things, and it's kind of amazing we're still around with all the different disasters that are going to happen. If we escape that one, and if you're willing to wait, just a mere 2 billion years, then we're in for a much worse experience, because the sun will be 15% hotter, and we will experience a runaway greenhouse effect and look like Venus and have a temperature of 1,000 degrees.
Oh.
Unless, of course, we can figure some way out of that.
What are the most likely scenarios, Professor, for man doing himself in, aside, and I mean by that, I guess, man doing himself in, or the no, I don't mean that. I mean the extinction of man, whether by his own hand or by another hand, a hammer from space, whatever. We've already talked about it. What are the most likely scenarios?
Well, I think it's hard to imagine. In order to completely get rid of, life is very robust, and that's one thing people should realize, is that in the history of the Earth there have been many mass extinctions, but none of them, as far as we know, have ever extinguished all life on Earth. It's amazing when you look at there have been times where there have been dramatic overhauls, but even there, some life forms have survived. So it's very robust. And now of course, there are a lot of life forms that are more robust than us, like cockroaches.
Yeah, I've been asking about us, though.
Yeah, us. So it's hard. What I was going to say is, it's hard for me to imagine anything that we would do that would completely exterminate us as a species. I can imagine getting rid of a civilization, but some humans would exist. But so I think the things that are likely to exterminate us as a species are likely cosmic in origin. And there, the one we've talked about, I think the most likely significant event will be, in fact, an impact from a large meteor asteroid.
Okay.
That would, and if one that was size 10 kilometers or so, maybe 100 kilometers across, if a 100-kilometer across meteorite hit the Earth, it would essentially evaporate all of the oceans, and it's hard to imagine much life surviving after that.
All right, now let's look at our own hand. We are deep into the human genome now. We're modifying. I heard the other day we actually created a virus for the first time. We actually created a virus. And, of course, people in the war labs are working on, viruses to vector things that, if somebody went oops and it got out, it could go raging around the world like a wildfire, just extinguishing life everywhere it went, and it would go everywhere.
Well, one could imagine biological accidents that do huge damage.
Yeah.
But again, if you look at any past examples of such things, they usually don't completely eradicate things. The plague killed many people in Europe, but there were people who were immune to it, and because there are mutations, and so you're right. I think Biological damage is a huge threat.
That was Mother Nature, though. I mean, if man puts his hand in and actually designs something to be aggressive enough and deadly enough to really to do the job, Mother Nature always leaves a little hole in there. but gee, we're getting pretty bright.
Yeah, we are, and I think we are likely to certainly create great changes. I like to be more optimistic, and I think that we will essentially redefine what we mean by life over the next century. We will, as we understand the genome, be able to, and by the way, at the same time as our computer technology enhances, my expectation is that we will be able to create life where it didn't exist before, and we'll be able to change what we mean by life. And a lot of people find that terrifying, but I think it's inevitable. And you're right, in the process we might destroy it as well. I think, as I said, if anything, we've learned that life is incredibly robust. It's been around continuously for 4.5 billion years, or not quite 4.5 billion, 4 billion years on the Earth, in spite of lots of disasters, and biological ones included. And so I'm less pessimistic about that, but I am certainly prepared to recognize that what we now think of as our present life form, and what we now think of, we tend to think of ourselves at the top of the evolutionary ladder.
Yes.
But of course, that's not true at all. We're just a branch, and what's next will affect it ourselves. And I actually expect, when I think of the science fiction future, that we will combine self-aware computers with biology to make new life forms.
Didn't we just, I think it was IBM that succeeded in teleporting a bit of light from here to there?
Uh-huh.
So then, did they really do that?
Well, yes.
They did.
Well, yes, they did. I mean, they picked a good word, right? Because, when you talk about a transporter or teleportation, everyone gets excited. And what they did is an interesting application of the laws of quantum mechanics to destroy a single elementary particle, in this case a photon, a piece of light,
right,
in one place, and instantaneously produce the exact same configuration somewhere else.
Boy, that sounds just like Star Trek.
It does, doesn't it?
Yeah, it does.
Now, the problem, there are lots of problems with that, however. First of all, it was a single piece of light, not a human being or a bowl of oatmeal. And in fact, the reason they were able to do that is they exploited the laws of quantum mechanics, which apply on elementary particle scales, and in this case, they used the fact that this particle was very carefully created and monitored and controlled throughout the experiment as an individual particle, so that it didn't interact with other particles, etc., etc., etc. Well, unfortunately, of course, we are not so carefully prepared, and things at macroscopic scales, human scales, are not carefully prepared quantum mechanical configurations. The particles in our body are colliding against other particles every second, and with the air, and all sorts of stuff. So all of the weird aspects of quantum mechanics that were exploited in that experiment, which are...
Well, I understand that if you were to transport a human being with that technology, you'd be jelly on the other end.
Well, you wouldn't be able to, be able to do it. The point is,
right.
You wouldn't, because you are exploiting at that scale phenomena that we can't experience at human scale.
Indeed so. But my question is that not perhaps the first step that will result one day, long from now, perhaps, though in teleportation for real?
I would argue no. And the reason is that the quantum mechanics is the weirdest thing. It's weirder than anything we've talked about. It's so weird, even if we know the mathematics of it, you can never truly understand it, because it's just particles behave so crazily on ultra small scales that everything you think is sensible goes out the window. For example, a baseball. I throw a baseball to you. If you're in the at the other end of a baseball field, well, of course it follows some trajectory from me to you,
yes,
right? You told us what the trajectory is.
Correct. Yes.
An electron that goes from one place to another.
Yes.
Well, you can show that in no sense does it follow any. If you don't measure it in between, if you just measure it where it started and where it ended, there's no sense in which it followed a single trajectory from one place to another.
Huh.
In fact, it traveled on many trajectories at the same time. That's insane, but it's true. Like it or not, that's the way the world behaves on small scales. Now, we can exploit that craziness, and that's exactly what this kind of experiment was doing, was exploiting that quantum mechanical craziness. But you can only exploit it on the scale where quantum mechanics where quantum mechanical phenomena are manifest, which is either very small scales or particles or configurations that are isolated from every other. Because the minute you tap a particle, the minute you observe it or the minute you affect it, you screw up all that quantum mechanical phenomena. It just goes out the window. And so in order to have that neat thing, that teleportation, you have to have something that's completely isolated and completely controlled. And therefore, I think the likelihood of transporting humans that way is the same as the likelihood of humans being able to walk through walls.
Yeah, but you know, a quantum computer might straighten all that out.
A quantum computer, by the way, this might help us make a quantum computer. A quantum computer is basically a computer that does many, many calculations at the same time.
Right.
And that's exactly what elementary particles allow you to do, because remember, they take many paths at the same time. So that is realistic, or at least you can imagine it. I don't really, I think there's been a lot of hype, but I think it's worth working on. That is realistic, but I think the idea of a transporter is electrons, by the way, tunnel through. That's something else particles do. If I take a ball and I throw it at a wall, it does one of two things. It bounces off.
Is it possible, Professor, that a quantum computer would lead us toward, if not movement between dimensions, at least perhaps communication or the extraction of information from other dimensions? Well,
first of all, other dimensions would have to exist, and we have no evidence that they do.
Well, you suggested the possibility.
Well, that one of the things that physicists are considering is the possibility there are extra dimensions. It's an interesting idea, but I do want to stress that we have no evidence whatsoever that they exist. But the quantum computer would operate in our universe using our laws of physics, and therefore, one of the aspects of quantum mechanics is, as weird as it is, it never takes you out of your own reality. Okay, and so there's limits to the weirdness of quantum mechanics as we understand it and as we can test it. And so a quantum computer would allow us to do many things in the sense of potentially, well, unfortunately, it would allow us to break codes, and that means that a lot of the codes that store money in banks and other things would be breakable, and we have to figure out new ways of keeping information safe. But it's not likely it certainly wouldn't be able to obviate the laws of physics as we know them.
All right. A lot of people want to talk to you. Much as I would like to continue, I've got to go to the phones a little bit here. On the international line, you're on the air with Professor Lawrence Krauss. Where are you calling from, please?
I'm calling from London in the UK. My name's Jeff. I called before.
Okay, Jeff, welcome.
Okay, thank you.
Hi.
I had some questions for Professor Krauss.
Yes.
Sure.
Okay, first of all, the idea of life transporting around, not so much intergalactically, but within our galactic, has actually been proposed by Marshall T. Savage. He reckons it could be done with about 1,000 years. Well, maybe yes, maybe no, but I certainly believe that we could travel to somewhere like Alpha Centauri fairly quickly, because it would only take us about a year to reach light speed if we accelerated at 1G.
If you accelerate continuously at 1G, it would take a year or two to reach light speed. That's a true statement.
Right, and
but of course you have to have the fuel that would continue to do it. That's the problem.
Well, now Alpha Centauri, though. I see the fuel problem again. Yes,
the fuel problem. I mean, you still got to have something that's accelerating you at 1G continuously for a year. Try it.
Yeah, but that makes an assumption that you're going to be accelerating something the mass of something like a space shuttle. But what if you could reduce the mass and inertia that was required?
Oh, absolutely. There's no doubt that the only sensible way to imagine sending things outside of our solar system to explore beyond it, it seems to me, especially if you want to do it in a reasonable time, is to have micro objects. To imagine intelligent chips that are minuscule in size, because when it comes to interstellar travel, mass is the villain.
Nanotechnology, then.
Nanotechnology is the only sensible way to consider doing that. I agree with you there completely.
And the other one was teleportation. Now, I always heard that maybe the biggest problem with teleportation, apart from the amount of energy, was that the breaching of Heisenberg's uncertainty theory. But I'm not so sure that would happen, provided that you didn't actually extract the information of either location or direction of the things that are being teleported.
Well, in fact, you are correct in the sense it's not that they get around the for your listeners, by the way, Heisenberg uncertainty principle says I can never know where an atom is and what it's doing at the same time, basically.
Mm-hmm.
I can know one or the other exactly, but I can never know both exactly. And you'd kind of think if I want to reproduce something, I would have to know both exactly, right, at the atomic level. But in fact, these kind of teleportation experiments get around that by actually never measuring the configuration that they're trying to reproduce. At any point in the process, they never actually make a measurement, and therefore they never the laws of nature allow it to be reconfigured exactly without you ever having had to measure it in the process. It seems like a swindle, but it's a swindle that works. So I agree that does not make teleportation of individual quantum states impossible because we've been able to do it. But unfortunately, all of my problems with transporting human-sized objects continue to be exist.
I agree with you. I mean, it is very, very difficult to imagine it scaled up to human size. But
or anything beyond a very carefully prepared quantum mechanical system, which is generally of order atomic size.
Sure. Thanks so much. And I have read your book. It's a very good book.
Thank you.
Okay, take care. Speaking of books, you've written quite a few. Let's see. Atom, a single oxygen atom's journey from the Big Bang to life on Earth and beyond. That would be your latest or your...
That's my latest.
Your latest,
book,
okay.
Yes.
And before that, Beyond Star Trek, Physics from Alien Invasions to the End of Time. Boy, you're good with titles. The Physics of Star Trek. So you were a Trekkie, huh?
Well, I never dressed up, but I certainly watched it.
Quintessence, the mystery of the missing mass. The Fifth Essence, the search for dark matter in the universe. And Fear of Physics, a guide for the perplexed. Very interesting. Star Trek was more than just another television show, wasn't it? I mean, somebody obviously had an awful lot of insight into... They must have had a theoretical physicist on staff someplace or another.
You'd think so, but they really didn't. I mean, Gene Roddenberry used to know a little bit, and they used to go talk to people at JPL every now and then. But and some of the people I've talked to, some of the writers, some of the art directors, like to read Scientific American. It's kind of amazing how often they kind of their intuition was very close to the real world, even when I think they really didn't know what they were doing. It's kind of amazing. One of my favorite examples is an early episode of Star Trek. I think the third episode, they go too close to the gravitational field of something that they call a black star, and they get sent back in time. Right?
Yes. Oh, yes.
And I remember looking at that and saying, well, that's okay. The writers didn't know the word is black hole, but they came pretty close. And then I checked the air date of the episode, and it aired about 6 months before the physicist John Wheeler invented the term black hole.
Isn't that interesting?
So, they almost invented the term. It's kind of...
What about the replicator?
Well, the replicator is a version of the transporter that just works on omelets and that sort of thing. And it takes. See, the idea is if I'm going to transport you, at some point I have to have your entire pattern stored in a computer, right? So I can recreate you at the other end.
That's right. Hopefully accurately.
Yeah, exactly. So why bother? So the replicator just sort of gets rid of the middleman. If I can, take your pattern, I might as well just store a pattern and use some atoms from something else to recreate it, and I can make a cup of coffee or an omelet.
And I would like to, I ran a very interesting story in the first hour. There's a company. This may just be totally out of your field, but maybe you'd comment on it. It's called Applied Digital Solutions, and they've come along with the first implantable chip in human beings that will be used for, they say, security going in and out of buildings and all sorts of applications in the private sector, even nuclear power plant security there and that kind of thing. You have a chip, and in fact, they say you could even buy and sell things with it.
Yeah, certainly I can imagine. I mean, we already sort of use chips for dogs, right? I mean, in a lot of places you can, it's a kind of identification for animals.
But now they're offering $50 discount to the first 100,000 people who go for the chip here.
And what's in it for the people? I shouldn't. I'm the eternal skeptic. What's in it for the people?
Well, I don't know. Ease of I don't know. Payment. I mean, you don't have to carry credit cards or something, and then you pay a monthly $10 database maintenance charge. God knows what happens if you get behind.
Exactly. If you stop paying,
that's right. Come back and get the chip. Society is moving in an interesting direction, isn't it?
Well, I mean, I think it. Well, I hope on good days, I think it is. Yeah. I mean, I think the future, there's going to be the next century is going to be full of incredible things, and it's also scary too.
Yeah. So I interview a very interesting man like yourself, named Dr. Michio Kaku. I'm sure you know him.
Yeah, I know him.
I'm sure you know him. And he maintains that. When you really press him to the wall, I mean, everybody tries to be an optimist, but he maintains when you press him to the wall that the odds of mankind surviving the discovery of element 92 and then on from there, are really terrible. What do you think?
Well, I think in order to imagine surviving and maintaining the kind of society we live in for any length of time is going to require a kind of concerted organization that I've never seen in human history before. I mean, we can't even get our act together, and in response to global warming, we have an administration that can't even look beyond the next few years. And as a civilization, we're going to have to deal with, in 100 years, a loss of fossil fuels, and so it's hard to. I hope that humanity will be able to coordinate itself, but it's easy to imagine many ways that it won't. And so, it's easy to be pessimistic.
All right. Back to the lines. Wildcard line. Hello, you're on the air with Professor Krauss.
Yes.
Where are you? Where are you?
Carson City.
Okay.
Capital of your state.
Yes, sir.
I had a question about the theory of relativity.
Okay.
Now, everybody, when they explain it as the ship leaving the Earth.
Uh-huh.
And when it goes away, time slows down for the ship.
Uh-huh.
What about when the ship returns? Will time then speed up again?
Well, it's a very good question. In fact, what I'm going to tell you is even more strange. Okay, so be prepared. So when the ship's moving away, you look at it, and indeed it looks like that clock is slowing down compared to you. But if you're sitting on the ship and you're looking back at the Earth, guess what you see? It looks like the clock on the Earth is traveling slow compared to your clock. It's completely reciprocal. So you might say, well, if that's the case, how can anyone age faster or slower than anyone else? It turns out that when the ship is traveling in one direction, it's completely reciprocal. When it's traveling back, it's again completely reciprocal, but it turns out all of the aging happens when it turns around. So, it is absolutely true that if you traveled out at near the speed of light for 100 years and then came back for 100 years, the person on the ground would have aged 200 years,
but you
wouldn't have aged hardly at all.
Yeah, but you just said the aging occurs as you're turning around. Why? Why?
Well, you have to take my physics class for me to tell you that. It's just it's a little complicated to explain in the radio, but it turns out that the actual here's the way to sort of understand it. Galileo and Einstein told us that two objects moving relative to one another, you can never prove who's moving and who's standing still, right? If you've ever been on a train on a train track and you look at the one nearby, sometimes you don't know when you're in a subway train whether you're moving or it's the one on the other side, right?
Right, of course.
And it's absolutely true. The laws of physics tell us you cannot prove that you're absolutely standing still and someone else is moving. You're just moving relative to one another.
Right.
Well, so the two observers are exactly identical as long as they're moving in uniform velocity. But the time when they become different is when the other observer slows down and turns around. Because when you slow down, you experience a force, G-forces. You get pushed up against the steering wheel, or you get pushed back into your seat when you speed up. And that's when you are different than the person on the ground. And that's, therefore, the time when all of the action happens. So that's what separates the two observers, is one had to slow down and speed back up again in order to make the round trip.
That's incredible. All right. East of the Rockies, you're on the air with Professor. Hello.
Art.
Yes.
Big fan. Ryan here in Kansas City.
Kansas City. Okay.
I'm hoping to hear the doctor's thoughts on some really interesting issues. He's touched on one already. Maybe he can quickly go a little more in-depth on the uncertainty principle and talk about the role that observation itself plays in affecting the motion of particles, but also ambient energy and how that might eliminate the need for taking fuel along on some trip that we take through space, but also here at home, eliminate the need for fuel here as well.
Well, those are all interesting questions. Let me see. Let me hit the Heisenberg one first. It is absolutely true that in quantum mechanics, when you observe a system, when you measure it, you change it. And again, it's absolutely crazy. Take that electron I was talking about earlier. Remember I said if you just measured at the beginning and the end, it didn't take just one trajectory between them, it took many. But if you actually observe it all the way along, you'll observe it to take only one. So you're actually changing things by observing it. And again, this isn't science fiction. We can measure it with real elementary particles. They behave differently if you measure them when they're going from one place to another than if you don't measure them. And it is strange indeed. Now, as far as the ambient energy issue, in terms of interstellar travel or even travel within our solar system, you're absolutely right that not having the fuel on board a spacecraft saves you tremendously. Because if you carry the fuel on board, then you need yet more fuel. Because the fuel weighs stuff, you need more fuel to transport the fuel, right? And it's a vicious cycle. So if you can somehow, beam energy or use energy from cosmic magnetic fields or something else to help power a spacecraft or solar sails, it is a much more efficient way of traveling throughout space. Now, as far as ambient energy on Earth, well, the best kind of ambient energy, of course, is the sun. And it's kind of sad and strange that we don't utilize that more. We do indirectly with our fossil fuels. It was solar energy that stored all those years in the fossil fuels. But one of the most sensible things to do would be, in fact, to recognize that the sun is a great source of energy and to try and utilize solar energy a lot more effectively than we are. And the amount of energy we would save by using solar energy would cost much less than the amount of energy it required to build new power plants.
And Professor, why do you think we're not right now on a mad scramble to utilize solar energy before it's too late? Why are we not doing that now? Why haven't we been doing that for quite some time?
Well, I guess I would have to say part of it is due to the fact that people like the President of the United States ran an oil company. and there's a lot of money to be made in oil.
No. It couldn't be that, could it?
I'm afraid money runs the world in science fiction and in reality as well.
Well, hey, speaking of the solar energy, it's brought up another question really quickly. How much did it cost for you to outfit your home with the solar panels I understand you have to...
Oh, you're asking me?
Yes, sir. Yes,
yeah,
sir.
Too much. It cost about $50,000. I did. I actually got off the grid, Professor. I put up solar panels and wind generators and all the rest of it. And the problem with it is, of course, that it's a nice thing to do, but it's not practical. In order for me to ever see a return on what I did, I'd grow old and gray and dead, and my children would have something of a life, and they still wouldn't see a recovery.
Yeah, it's not practical now, but of course, if there was a market for everyone to do it, you can bet the cost would be a lot less, right?
Well, I guess the market doesn't get generated until the price goes way up.
I think it's a cycle. I think if there was, first of all, obviously more R&D being put in, the cost would be less. But I also think if there was the potential to sell to a huge market, you'd see the cost go down. But,
yes.
I mean, but on the other hand, there are a lot of people who don't outfit their whole house, but for a reasonable price, certainly reduce their fuel bills. One of my colleagues has, even in Cleveland, which certainly doesn't see the sun like you see the sun where you are, even there still ends up reducing his power bill, and his cost is more like $2,000 to $5,000.
Mm-hmm. All right. West of the Rockies, you're on the air with Professor Lawrence M. Krauss. Hello.
Hi, Dr. Krauss.
Hi.
Hi. I have a question about another one of Einstein's theories. It's called frame dragging. That has to do that Frank Tipler, who I think was a mathematician.
Yeah, mathematical physicist, yeah.
Yeah, he had a solution to Einstein's frame dragging that if you were to travel around supposedly 3 lined-up neutron stars that were traveling, spinning extremely fast, that you'd, in a sense, have a time machine. But I know that you said that it would be really hard to go out and build wormholes and these sorts of devices because the energy involved, right?
Uh-huh.
So, what about instead of an actual machine traveling in these 4-dimensional spirals, instead of sending radio signals, suppose like bouncing it around the event horizon of a nearby black hole? Does that make any sense?
Well, no. in the sense that, I mean, a black hole alone is not exotic enough to allow, it's a very exotic object, but a black hole alone is certainly not exotic enough within the context of general relativity to allow time travel. Certainly not outside the black hole. What happens when you get inside the black hole, eventually all bets are off, because near the singularity, the center, again, the laws of physics break down, so I can't say what happens. But you don't want to fall in a black hole if you care about the future. You probably want to stay outside of it. And there we can solve the equations, and a single black hole, nothing you do around it around a single black hole will allow time travel. You need really exotic configurations, and people have thought of them and imagined the possibilities, and maybe those possibilities do exist in the universe. We don't know.
And in our lifetimes, we likely will not know, will we?
Yes, I think that's a true statement. We likely will not know, but of course, you never know what's around the corner. I mean, that's why people like me, go into work every day.
Is it possible, Professor? I've been told that the so-called theory of everything might be, I don't know, short as your thumb. Might be some short little equation that will suddenly open all the doors.
What's remarkable about physics is that when eventually, something that's really what appears to be complicated, when you understand it correctly, is usually can be understood pretty simply, and so there may be a theory of everything that is you could put on a T-shirt. Maybe we'll see. I'm not going to bet on it, but it's a possibility.
Wildcard line, you're on the air with Professor Krauss. Hello.
Hi, my name's Claudia.
Well, Claudia, I can barely hear you. You're going to have to yell at us, huh?
I'm from South Lake Tahoe. My name's
South Lake Tahoe. All right, I can barely hear you, so go ahead.
Oh, okay. I have a kind of a theory, but it's in a spiritual sense to get through that wormhole.
Uh-huh.
If the universe can be traveled by out-of-body, experience like astral traveling, which is when the body is like returning.
Yeah. Mm-hmm.
Spirit body.
Yes.
Say the matter turns into energy, which then turns into the light body with consciousness, right? And then the light body with consciousness could endure the speed of light through the wormhole, right?
All right. Well, let's boil all this down to I guess a broader question, and that is, Professor, isn't it possible with the directions that we're moving that one day science will, in effect, meet religion in some way, in the sense that we are, of course, energy. We have energy, and that energy does not, of course, cease to exist. It continues in some form or another, in some way or another, and is it not plausible that there's some sort of conscious continuance?
Well,
it's a bad question here.
As the other question was, I think I have to say that this astral stuff, as far as it doesn't hold water when it comes to the laws of physics as we know it. But
I know.
The idea of whether consciousness could exist, again, there's no. It is a reasonable postulate, although we don't know for sure. But it is not unreasonable to imagine that we are nothing other than the sum of our electrons and protons, and that our thoughts are, it's all chemistry.
Yes.
And if that's the case, when the chemistry ceases,
we cease.
Just like when you unplug a computer, just like all the computers that are sitting around me dead right now because I have no power here. And
you still have no power.
I still have no power.
Through the entire program, no power. That's amazing.
Power. Yeah, it's amazing. But and so I would bet that that's the case. That you turn off the power and the consciousness goes just like the computers do.
So if you had been the scientist sitting in the seat that Jodie Foster sat in, getting the question that was going to get you the ride, you'd be staying home.
Well, yeah, I guess I would. Yeah, I guess I'd be. Carl Sagan and I kind of shared that, I think. Yeah, and I think it's just. What amazes me about the world is that we can understand so much of it, and it's miraculously interesting with simple laws of physics. And I have not yet seen any evidence to go beyond the laws of physics into anything supernatural to understand anything I've ever studied in my life. That doesn't mean it doesn't exist. Okay, it just doesn't mean I haven't seen any evidence for anything, and so therefore, unless there's some evidence, I'm the eternal skeptic, I think.
Well, there are some very legitimate scientists that have suggested that the evidence of UFOs, while shaky in its bulk, at some point, at some small percentage, justifies a very scientific inquiry, perhaps even demands one.
Well, I think scientific inquiry into anything is a good thing. I think what I understand of the situation is that people say there's some things that many things can be easily explained away, other things cannot be so easily explained away.
Yes.
But that doesn't make them likely. It just means that no obvious explanation, and you have to look for less obvious explanation.
Which is what science does.
Yeah.
We're at the end of the interview. Professor, it has been an absolute pleasure. I hope everybody goes and researches on the web and buys your books. And
it's been a pleasure for me. Even here in the dark.
Professor, go to the light.
Yeah, thanks.
Go to the light. Good night.
Good night.